All right, this is Lab 6, Magnetic Molasses for Physics 2212. The purpose of this lab was to observe what occurs when a magnet is dropped down an electrically conductive tube of aluminum foil. And after taking several measurements in the real world, a model of the lab was made in GlowScript. And the results were that the average time it took to fall in real life was 2.04 seconds, and the model's predicted time to fall was 13.78 seconds. So some key concepts were Biot-Savart's law, and that describes the magnetic field at any point, and mu is the magnetic dipole moment in that equation. And we have Faraday's law, which describes how a change in magnetic field produces a voltage or EMF, which relates back to Ohm's law. And then we have Lenz's law, which says that an induced current will create a B field that opposes the change in the original magnetic flux. Right, so here's the experiment. We got the initial conditions were that the system was the bar magnet and tube, and the surroundings were everywhere outside. We had a magnetic dipole moment of roughly 7.265 amperes times meter squared. And this was calculated from the previous lab. And then we got the tube dimensions and the times it took to fall. The average time was about 2.04 seconds. All right, so here we have the computational model. Here are just some constants that we're defining at first, like the dimensions of the tube and the resistivity of the aluminum, and also the mass and magnetic dipole moment magnitude of the magnet. All right, so here now we have the function that creates the magnetic field of the bar magnet on the left. This is just writing out the equation of the magnetic field at any point. And then we have the calculation for the magnetic flux. And then we have just some, that's the derivative of the flux per time, which will calculate the EMF. And then we have on the right the force of gravity, and then computing the typical B field at each rin. So that's like the more formal equation, and then it gets the force. So after modeling all this out, we get the end result, which is that it took about 13.783 seconds. But this is very different from real life. And it could have been because that we assume that the forces were only the magnetic field and gravity, and the dipole moment may not have been aligned with the tube. And we also could have miscalculated the dipole moment for the previous lab, which is much more likely. All right, so red means clockwise and blue means counterclockwise, and you can tell the currents are induced to create a magnetic field that opposes the direction of the change in magnetic flux. And if we flip the magnet around, the currents would be reversed. The real-world system shows a much faster time than the computational system. If the calculation of the dipole moment were smaller, then we probably would have seen a more accurate computational system. And the shape indicates that the strongest force on the bar magnet is the force of gravity, which makes sense because although the magnetic force is equal to the force of gravity in the tube, it doesn't equal it after, and the force of gravity eventually wins. So what if the resistivity of the conductor were reduced to almost zero? Then the current would increase significantly by Ohm's law, and the magnet would fall slower due to Lenz's law. And if there were any holes or slots cut into the tube, then they wouldn't really look like rins. And the rins in the model wouldn't really look like rins, and the magnet will fall through much faster because this would equate to an open circuit. All right, thank you.